In this video, we discuss exponentiation in groups. Our exponents will be integers, so it's probably good for us to start with a few facts about integer divisibility and some divisibility notation. Here, a, b, c, and n are integers, and n is going to be positive. Our first bullet is some notation that indicates when one number is a divisor of the other. So a vertical slash b is not asking us to make a computation, rather it's simply a statement that a divides b. So for instance, I might write 2 divides 6, which is a true statement, but 2 does not divide evenly into 7. Okay, the next bullet point has to do with congruence notation. So we say that a is congruent to b modulo n, exactly when n is a divisor of b minus a. Third, we'll need some notation for the greatest common divisor of two integers, and there are a number of different possible notations for that, but our book uses a comma b in parentheses to denote a greatest common divisor of a and b. And now a few facts about divisibility. If a divides evenly into b times c, and a and b are relatively prime, meaning that their greatest common divisor is 1, then a must divide evenly into c. Another theorem is that if a divides into c and b divides into c evenly, and a and b are relatively prime, then the product a times b must also divide evenly into c. So this first theorem is something that we're going to need in the course of these slides. The second theorem we will not use in the course of these slides, but it could be useful to you in your homework for this section. Now we introduce exponential notation and laws of exponents in groups. Regarding notation, the very first thing we're going to do is drop the ever-present use of this star or asterisk to denote the product of two elements in our group. From here on forward, we're going to drop that star and just write x, y together to indicate that we mean to multiply x and y in our group. Now in additive groups, like the integers or the integers mod n, we will instead write x plus y to combine two elements. Now on to exponential notation. The first thing is that when we take a group element and raise it to the 0th power, we're going to declare that to be the identity in our group. And then if n is a positive integer, x to the n is just going to mean x times x times x over and over again with n occurrences of x. All of these multiplications occurring within the group G. And then x to the minus n is just going to mean x inverse raised to the nth power. So that is n occurrences of x inverse. Now we have laws of exponents in a group, and they should look familiar to you because they are the exact same laws of exponents that we know and love in our familiar arithmetic. So the first one, if you take x to the m plus n, that's x to the m times x to the n. And if you take x to the n inverse, that's x to the minus n. And x to the m to the nth is x to the mn. So here we have an example of a group, and we're going to take some powers of elements in this group. Well, you'll have to trust me that this is indeed a group. And if you look at the table, you can see that the identity in this group is 1. Right? If you look across this first row and first column of the table, you should be able to see that the identity in this group is 1. In fact, you can also tell that this group is abelian The way that you can tell that is if you look at the body of this table and reflect across the diagonal that runs from upper left to lower right, then that will preserve the table. So that means that this group is abelian. So let's start taking some powers of elements. In fact, let's start with 2. And we'll raise it to the first power. That's easy enough. That just gives us 2 back again. And then 2 squared is 2 times 2, and I look in my table and see that 2 squared is 4. So far, so good. And then I take 2 cubed. Well, 2 cubed should be 2 squared times 2. But we know 2 squared is 4. And now I look in the table to compute 4 times 2, and I get 1, which you might recall was our identity. Now let's take 2 to the 4th power. So that is 2 cubed times 2. But 2 cubed, remember, was 1, so that's 1 times 2, which is 2. And now, if you could reach through your computer screen, you'd want to stop me from computing any more powers of 2 in this group, because you can see that we have started to repeat our powers of 2. So really, there are only 3 powers of 2 in this group, namely 2, 4, and 1. What if we try some other element? Like, let's suppose we start with 3. So if I take 3 to the first power, I get 3. 3 to the second power, I look in the table, and I take 3 times 3, I get 2. Take 3 cubed. So that's going to be 3 squared times 3, or rather 2 times 3. And I look in the table, and I see that that's 6. And then 3 to the 4th would be 3 cubed times 3, but 3 cubed is 6. So 6 times 3, which is 4. And then 3 to the 5th is going to be 4 times 3. And I look in the table and I see that 4 times 3 is 5. And now finally 3 to the 6th is going to be 5 times 3. And lo and behold, when we take 5 times 3, we get 1. So notice that our powers of 3 did eventually cycle through and return to 1, but it took a little bit longer this time. And in fact, if you look at the list of powers of 3 that we obtained here, we achieve every single element of this group. Right? We achieve 1, 2, 3, 4, 5, and 6 as a power of 3. So groups like this, where every element can be expressed as a power of a single element, is called a cyclic group. We'll be talking quite a bit more about cyclic groups in the future. Okay, now we can also raise numbers to, or group elements to, negative powers. So let's suppose we wanted to compute 3 to the minus 4th power. What would that be? Well, we know one way to calculate that would be that this is 3 to the minus 1 power to the 4th. Okay, now what is 3 to the minus 1 anyway? Well, that's just the inverse of 3 in this group. So I go here to my row that's headed by 3, and I read across until I see a 1. And then I look up and I see this 5 here. And that tells me that 5 is the inverse of 3. So I'm supposed to compute 5 to the 4th power. And if you do that, just like we did on the left part of this slide, you should wind up with 2. Okay, now another way to compute 3 to the minus 4th would be to write this as 3 to the 4th to the minus 1 power. Now 3 to the 4th we already saw on the left part of the slide, that's equal to 4. So I'm taking 4 to the minus 1 power. Now 4 to the minus 1, that's just the inverse of 4 in this group. So I go to 4 as a row header, I read across until I see 1, which is my identity. I look up and I find 2 as being the inverse. So lo and behold, we achieve 2 just as we should have. In this next example, we're taking powers of 2 and 3 in Z10. The first thing that we need to notice about this setting is that Z10 is a group under modular addition. So this is an additive group, and in an additive group, our notation for exponentiation changes a little bit. So for instance, if I take 2 and I raise it to the nth power in this group, quote unquote, what is it that I'm doing? Well, we're applying the operation of addition over and over again to the number 2. And ordinarily, when we apply addition over and over again, we write that as a multiple. So we would essentially be taking n times 2 in this group, where n times 2 means we're taking 2 circle plus 2, circle plus 2, again and again with n occurrences of 2. So 1 times 2, if we just take a few powers of 2, 1 times 2 is 2. 2 times 2 is just 2 plus itself, which gives us 4. 3 times 2 in this group would be 2 times 2 plus another 2, so that would be 4 plus 2, which is 6. 4 times 2 would be 3 times 2, which is 6, plus another 2, which is 8. And then finally, something different happens. We get 5 times 2, which is 4 times 2, or 8, plus another 2. Now in Z10, 8 plus 2 is going to be equal to 0, which is our identity, and then our powers of 2 repeat from there. So the only powers of 2, or rather multiples of 2 in this additive group are 0, 2, 4, 6, and 8. So now we're also instructed to take some powers of 3. Why don't we take 3 to the minus 4th power? Okay, now we need to interpret what that means in terms of additive notation. So that could be maybe interpreted as minus 4 times 3, or rather interpreted as 4 times minus 3. Okay, now we're ready to do this, but first we need to know what minus 3 is. So we need to know that the inverse of 3 in Z10, and that turns out to be 7. So we're really taking 4 7s, adding them together. Okay, so let's compute 4 7s. So 7, well, that's just 7. And then 2 times 7 would be 7 plus 7, which is 14. That leaves a remainder of 4 upon division by 10. 3 times 7 is 2 times 7 plus 7, so that's just 4 plus another 7, which is 11, which is really 1 in Z10. And then finally 4 times 7 is 3 times 7, which is just 1, plus 7, which would be 8. So 3 to the minus 4th in this particular setting is going to be 8. it should be added here that this computation that we just made, the quote-unquote 3 to the minus 4 calculation, when it boils down to computing 4 times 7, we went down here and made a computation involving repeated additions. You can arrive at this same answer, 8, by just simply multiplying 4 and 7 together in the integers to obtain 28, and then divide by 10 to get a remainder of 8 for your final answer. In our previous examples, you might have noticed that we took some group elements and we raised them to powers. And one thing that happened was that eventually these powers would be equal to the identity, and then the powers would begin to repeat themselves. This is a phenomenon that we want to investigate in some detail. We begin to do that here in this definition. So we let G be a group and X be an element of G. We say that X is an element of finite order if X to the M is the identity for some positive integer M. Then, if X has finite order, we say that the order of X is the smallest positive integer n, such that X to the n is equal to the identity. So the notation for this special number n, which is the order of the element of X, is this script O of X. So in this instance, we would say script O of X is equal to n. Now finally, there are infinite groups that have elements that when you take their powers, they don't ever come back around to the identity. So if X is one of those elements and it does not have finite order, then we say that X has infinite order. Okay, you might recognize this group from several slides ago. We're going to compute some orders of elements in this group. And maybe we should begin with 2. So let's start taking powers of 2 and see what happens. So if we take 2 to the first power, we get 2. 2 to the second power, that's 2 times 2 in our group, which is 4. So this should be looking familiar to you. And now when I take 2 cubed, that's just 4 times 2. But in this group, when I take 4 times 2, I get 1, which is my identity, right? So 3 is the smallest positive exponent I can put on 2 in this group to obtain my identity, which is 1. So what we say is that the order of 2 in this group is equal to 3. Okay, maybe we can also do this for 6, right? 6 to the first is 6. And then when I take 6 squared, well, I take 6 times 6 in the table and it gives me 1, which is the identity in this group. And so I would write down that the order of 6 is equal to 2. Because 2 is the smallest positive exponent I can put on 6 in order to get the identity. Now you might remember that a couple of slides ago we took powers of 3. So we started with 3 to the 1, which was 3, and then we did a whole bunch of stuff, and the first time we wound up with the identity was with 3 to the 6. That turned out to be 1. And that was the first time that we ever achieved 1 as a power of 3. So in this instance, we would say that the order of 3 is equal to 6. Okay, once again, we're to compute orders of some elements in a group. This time, however, we're going to be working in Z10, which is an additive group. So to compute the order of an element in an additive group, I'm looking for the smallest multiple of the element that gives me the identity. So for instance, let's start with 5. right? If I take 1 times 5, I get 5. If I take 2 times 5, what does that mean? Well, that means I'm adding 5 plus 5 in Z10, and that gives me 0, which is my identity in Z10. And so we would say in this instance that the order of 5 is 2, because that's the smallest multiple of 5 that will give me 0, our identity. So we've handled 5. Let's now do 3. So 1 times 3 is 3. 2 times 3, that's 3 plus 3, which is 6 in this group. 3 times 3 is going to be 9. 4 times 3 is 9 plus 3, which is 12, which is really 2. And then 5 times 3 is 2 plus 3, which is 5. And then we continue over here. 6 times 3 is going to be 8. 7 times 3 is going to be 1. 8 times 3 will be 4. 9 times 3 will be 7. And finally, 10 times 3 is going to be 0. So we had to go a long time in our multiples of 3 before we ended up back at the identity, namely 0. So in this instance, we say that the order of 3 is equal to 10. So here, this number 3, its multiples give rise to every single element in Z10. So Z10 is also a cyclic group. Okay, now maybe we'll want to pause the video and you all can compute, say, the order of 2 and the order of 1. Okay, I'm now assuming that you've paused the video and done a little bit here in computing powers, or excuse me, multiples of these elements. So let's start with 2. So I take 1 times 2 and I get 2. 2 times 2 is going to be just 2 plus 2 in this group, which gives us 4. 3 times 2 will be 6. 4 times 2, which is 2 circle plus 2, circle plus 2, circle plus 2, gives us 8. And then finally, 5 times 2, that's going to be 8 plus 2 in our group, which gives us 0, which is our identity. So the smallest multiple of 2 that gives us the identity is 5. Okay. And then if you look at multiples of 1, you should be able to compute that the order of 1 is 10. Right, you get 1, and then 1 plus 1, and then 1 plus 1 plus 1, and so on. And it takes 10 multiples of 1 before you return to the identity, namely 0. Here we have a theorem that can make computing the order of a group element easier. So we start with a group G and an element X in G, and then we let M and N be positive integers. The first result says that the order of X inverse is exactly equal to the order of X. The second result says that if the order of X is N and X to the M is the identity, then N must divide evenly into M. And then finally, if the order of X is N and D is the greatest common divisor of M and N, then the order of X to the mth power is N divided by the greatest common divisor, D. Okay, so we're going to try to prove all 3 of these results. Part A is an exercise that you will do in your homework. For Part B, what we want to do is divide M by N. And the division algorithm tells us that when we divide M by N, we get a unique quotient and remainder, where that remainder must be bigger than or equal to 0 and strictly less than n. So now we have this equation. We begin with the identity, and we're told in part B that x to the m is the identity, so I know that e is x to the m. But now we've divided m by n to obtain that m is nq plus r. And then we can use our laws of exponents to arrive at this step. But now we recognize that x to the n in part B must be the identity, because n is the order of x. So x to the n to the q is just the identity to the qth power, which is just the identity. So we're left with the identity times x to the rth power, which just gives us x to the r. Okay, now what does all of that mean? It's telling us that x to the r is the identity. Now, if r were bigger than 0, then r would be a positive integer less than n, where x to the r is the identity. But we know that n is the order of x, and therefore n is already the smallest positive exponent we can put on x in order to get the identity. So r cannot be greater than 0, otherwise it will contradict the minimality of n. Therefore, r must equal 0. That's the only other possibility for r. And if r is 0, then that means that m is equal to n times q, which means that, that n is a divisor of m, and that's exactly what we wanted to show. So now, moving on to part C, we're trying to show that the order of x to the m is n over d. And so that means that we need to do two things with n over d. First of all, we need to show that x to the m raised to the n over d power is the identity, right? And that's shown right here. And then we need to show that n over d is the smallest positive exponent we can put on x to the m in order to get the identity. So now let's suppose that we have some positive integer t, where x to the m raised to the tth power is the identity. From part B, we know that n must divide evenly into m times t. And then because d is the greatest common divisor of m and n, we can write m as and n is a multiple of d, where p and q are relatively prime. So in that instance, if n divides m times t, we can translate that into q times d dividing p times d times t. If you cancel the d's, you get q divides p times t. But remember that q and p are relatively prime, and therefore we had a theorem earlier in this video that said that q must then divide t. But q, if you go back here, if you solve for q, you know that q is n over d. And so that means that n over d divides t. Now, who cares about that? Well, if t is a positive integer and n over d is a positive integer, and n over d divides evenly into t, then that means n over d is less than or equal to t. So that means that if there's any positive integer power that you put on x to the m in order to get the identity, that positive integer power has to be at least as big as n over d. And so that tells us that n over d must be the order of x to the m. Now we're going to use the previous theorem to compute some orders of elements. So in our first example, we have an arbitrary group G with an element x, and we're told that the order of x is 18. We want to compute the order of 4 and the order of x to the fourth and the order of x to the fifth. So first let's handle the order of x to the fourth. So in this instance, our value of n, that is the order of x, is 18. Then the power of x that we're considering is the fourth power, so that means that m is going to be 4. And then we have to compute the greatest common divisor of m and n, so that would be the greatest common divisor of 18 and 4, which is 2. And now if we use the previous theorem, this tells us that the order of x to the fourth is n over d. But if we take n over d, we get 18 over 2. And that's 9. So that's the order of x to the fourth. Now, order of x to the fifth is nearly the same thing. In this case, again, n is 18, but now our exponent is 5. And d is going to be the greatest common divisor of 18 and 5. And that's 1. And so the order of x to the fifth is n over d, which is 18 over 1, and that's just 18. Okay, so that's the order of x to the fourth and the order of x to the fifth. Okay, now in the next example, we're computing some orders of elements in Z30, and we need to remember now that Z30 is an additive group, and that means that exponents are now going to become multiples. So the first thing that we might observe in Z30 is that if we take the order of 1, what's the smallest positive multiple of 1 that will give 0 in Z30? And it turns out that it is 30. Now we want the order of 3, and it might be good to point out that 3 is just 3 times 1. So in this instance, our value of n, so first of all, our value of x, say, from the previous theorem is 1. The order of x, that is n, is equal to 30. So this is an n here. M, which is the power of x, or rather in this case the multiple of x we're considering, is 3. And d is the greatest common divisor of n and m, which is 30 and 3. So the greatest common divisor of those two numbers is just 3. And so from there, we see that the order of 3 is n over d, which is going to be what? 30 over 3, and that's going to be 10. Okay, so that's the order of 3. And a similar computation will give you the order of 4 and the order of 18. I don't think I have room here on the slide to do the order of 18. We might do the order of 4 here. So again, the order of 4 is the order of 4 times 1. So it's 1 plus itself 4 times. And that's going to be n, which is 30, over d. Now d is the greatest common divisor of 30 and 4 this time. And that common divisor is going to be 2. So that's 30 over 2, and that's 15. So that should be the order of 4. Now look, if you don't believe this stuff, what you can do is just take 4 and add it, continually add it to itself in Z30, and you should find that when you do that 15 times, you arrive for the first time at 0. Sometimes when we look in a group, we can find an element in that group where if we just take powers of that one single element, we get the entire group from those powers of that one element. Groups like that are called cyclic groups. Every element in a cyclic group is a power of some single element x. That single element is called a generator for my cyclic group. And we would write G equals angle brackets x. Now sometimes cyclic groups can have more than one generator, but they have to have at least one generator. Okay, some examples of cyclic groups. Both the integers under addition and the modular integers under addition are cyclic. And in fact, they're generated by, and each of them is generated by 1. Okay, two groups that are not cyclic, or familiar groups that are not cyclic, are the real numbers under addition, and also the collection of 2 by 2 invertible matrices under matrix multiplication. Those groups are not cyclic. And in this third example, I'm showing you the very smallest non-cyclic group. It's called the Klein 4 group. It's a group of 4 elements. And if you look, you'll see that every element in this group is of order 2, which means that if I take any value of x in this group, the only distinct powers of x are going to be the identity and x itself. So this is not cyclic. So, right, so the order of E is 1, and the order of every non-identity element is 2. So there's no element of this group that can generate the entire group. We finish our video with a theorem about cyclic groups. So we let G be a cyclic group generated by an element x. The first thing is that this group G must be abelian. So every cyclic group is an abelian group. The second result says that if the order of x is equal to n, then 2 powers of x are equal if and only if their exponents are congruent modulo n. And this has the additional charming property that the distinct elements of G are then e x squared up through x to the n minus first power. And then the third result says that if the order of x is infinite, then the powers of x are different whenever the exponents are different. And then finally, we see that the size of the set G is exactly equal to the order of x. Now, we're not going to prove all of these results. In fact, we're only going to look at parts A and B. For part A, if you start with 2 elements y and z in our group, then y and z both must be powers of x, because x generates this cyclic group. And then if you want to compute y times z, that's just x to the j times x to the k, and then our powers, our laws of exponents take over here, and we are able to conclude that y times z is equal to z times y. Therefore, the group is abelian. Now, for part B, let's suppose that we have x to the j equaling x to the k. If you multiply by x to the k inverse on both sides of that equation, you wind up with E being equal to x to the j times x to the k inverse. And then using our laws of exponents, we see that that is actually equal to x to the j minus k. So that means x to the j minus k is equal to the identity, and since n is the order of x, we had from a theorem a little while ago that n must divide evenly into j minus k. And that means that j is congruent to k modulo n.